Notes 3. Answer those 5 questions by looking at that graph. All right, so one little change there was we didn't want a side limit for number 7. So check those answers. Kind of a quick question here on 9 and 10. What about this? Does the limit as x approaches negative infinity equal, question, I'm not saying it does, I'm asking, the limit as x approaches positive infinity?
Yeah.
What do you think? Why do you say yes?
They're both the same, are they not?
What are they?
They're both. Yeah.
Okay, so they both go to negative infinity. They're both does not exist. So in some ways you can say, yeah, they're kind of doing the same thing, but you can't say that D and E equals D and E. That doesn't work.
It's not equal. No.
So you can't say that they're equal to each other. Okay, so they're doing the same thing, but officially you can't say, oh, that doesn't exist and that doesn't exist, so they're the same. Like, well, no, they didn't even exist. They can't be the same if they don't exist. That's kind of a weird side note. All right, one-sided limits are hopefully easy at this point when you're looking at a graph, right? Like every one of the ones like I called on you guys, you all got them right, from the left, from the right. No big deal when you have a graph. But when you want to find a one-sided limit from an equation, things can get a little more difficult. So one-sided limits from equations, that's what we're doing today. Now, the first go with limits is always, and I'm still trying to drill this into my calculus students' heads, when you first get a limit, try substitution. Because in calculus we've learned a few more things, but there's still some where substitution works. So try substitution, and basically if you get a nice number, that's your answer. If you do not get 0 in the denominator, then you're good. So let's try. X approaches 2 from the right, but that means we're getting close to 2. Let's not worry about left or right. Let's just plug in 2 and see what happens. So 4 minus 4 is 0. 4 plus 4 is 8. Hopefully we're all okay with 0 in the top versus 0 in the bottom by now. 0 in the top is okay, right? That's the okay answer. So that's 0. Let's see. 3 from the left, but first pass, I'm not going to worry about from the left. I'm just going to plug in 3, and if I get an answer, that means it also worked from the left. So let's just plug in 3. So 1 over 27. Yeah, that works. We're good. So first attempt is basically ignore the left or right thing and see if you get an answer. Because if there's an overall answer, that means it was from the left and from the right. Oh, trig. Sine of pi over 3. I got to draw the picture every time. Maybe it's just me. Sine of pi over 3 would be root 3 over 2. Cosine of pi over 3 would be 1/2. So I'm going to get an answer here. It's just going to take me a minute to get there. You know what? Let's do the fraction clearing thing like we did yesterday. Multiply top and bottom by 2. And we get root 3 over 3. And that's a perfectly acceptable answer, so we're good. So as always, try substitution first, even if it's a left or right limit. Basically, ignore the left-right thing. Try substitution. If it works, great. The next line on the notes, though, most of the time, however, meaning change is coming, you will get a 0 in the denominator or an indeterminate form, so you've got to do something. So if I plug in 3 minus 5 over 3 minus 3, that's negative 2 over 0. It's like, well, what in the world does that mean? It's not indeterminate, because indeterminate has to be 0 over 0 or infinity over infinity. So it's not indeterminate. This is, if we divide by a really small number, we get a really big number. But which one is it? Well, it's one of them. So how do we figure out which one it is? That's the point of today. So flip it over. This is where things get a little bit interesting and students start throwing things at me, at least in their mind. Not literally, don't do that. But still, calculus people, Mr. Wolf, are you doing that funny math again where you're just like making stuff up? Like, no, I'm not making stuff up. But I understand the confusion. Plug in a slightly larger or smaller number. All right. If you get a non-zero number in the numerator and a 0 in the denominator. So if you get 7 over 0 or negative 2 over 0, then you have a vertical asymptote. Right? That you remember that. If they canceled, then you had a hole. But if they didn't cancel, you had a vertical asymptote at that value of x. Let's pause there and look at number 4. This is the same one from the previous page. Forget the limit stuff. This thing has a vertical asymptote at x equals 3. Right? You remember that from long ago? Doesn't cancel, so it's a vertical asymptote. So that means at x equals 3, well, it's going to infinity, but I don't know if it's positive infinity or negative infinity or it's like one of each. Like, I don't know. So we need to determine if the answer is positive or negative infinity. So back up to this one. 3 minus 5 is negative 2. 3 minus 3 is 0. Plus or minus infinity. That's not like it's both of them. It's like, which one is it? We have to pick. To do this, plug in a slightly larger number if you're coming from the right, slightly smaller number if you're coming from the left. Okay, here's where things are going to get interesting. So we're coming from the right, so let's plug in something a little bit larger than 3. What's a little bit larger than 3? 4 is bigger than 3, but I don't want to be that much larger than 3. I want to be just a little bit larger than 3. Let's go 3.1. That'll be good enough for us. If you want to get crazy, you can do 3.01 or 3.001 or on and on. So 3.1, because I'm coming at 3 from the right, so I'm getting close to 3, but I got to be more than 3. So 3.1 minus 5. I'm not really concerned about the top. That's still negative 2-ish, negative 1.9. What I'm really concerned about is the bottom. So it's 0.1, but it's, if I did 3.01 or 3.001, it's getting to be really, really small. And this is where the calculus students and maybe the pre-cal students, like, come on, you're telling me that 3.1 minus 3 is very small? Since when is that a math answer? But it's not just 3.1, because we got to get closer and closer to 3. So 3.01, well, that'd be very smaller, or veriest smaller, or however you want to phrase that. We're getting smaller and smaller. But the point we're doing, very small. Is it positive or negative, though?
Very small.
It is very small,
Positive.
but it's positive. And that's why we're doing this. Well, be careful. What's the numerator? Negative. So negative over positive is negative, and we already said it was infinity, so it's negative infinity. Because the sign, so the very small business, I'm not concerned about very small, I'm more concerned about positive or negative.
So So very small isn't like a part of the answer.
No, that's not the answer. That helps us toward the answer. Now, I see from your faces you feel the same way about this as my calculus students do.
If it's a negative, because it was a negative 2 originally on top.
Yeah, it was negative in the top and positive in the bottom.
No, I mean, yeah.
So that makes negative.
Right, but negative 2 over 0, would that ever be? Is it just negative?
But it's not negative 2 over 0, right? Because we don't actually get to 3, we just get close to 3.
I know, I mean, would it not just be negative to negative because it's negative over positive? Or...
Yes.
I'm saying...
I guess I don't understand your question.
I'm saying from the negative 2 over 0, when we originally did it.
So he's saying...
Oh, no, you can't tell from here just because that's negative.
Oh, okay.
Yeah. Let's keep going. Number 5. If I plug in 4, 4 minus 5 is negative 1. 4 plus 2 is 6. 4 minus 4 is 0. So I've got infinity. But here's your question, Will. You want to skip all that and say, look, it's negative, right? So negative infinity.
Yeah, why not?
Let's see. I'm coming at 4 from the left. So what should I plug in? What's a little less than 4? 3.9.
Oh, it's going the other way.
Or 3.99 or 3.9999999 or however many nines you want to throw in there.
Right, so it's going to be positive this coming in.
So, you know what? I'm not even worried about the top. I'm just going to say the top is still negative 1 and 6. Or pretty dang close to it. Because I'm only worried about the bottom. I just need to know if the bottom's negative or positive.
I think it's going to be positive. I mean,
3.9 minus 4.
Negative. Very small.
Super small. Very small. However you want to phrase that. Almost 0. But it's negative.
So that means it's positive.
So I've got a negative 6 over a negative small.
Wait, so if we don't have like small written on our paper, we can just take off the point?
No.
Or like, how does this work?
But okay, so you don't have to write small, but you do have to be thinking there's a 0 in the bottom, but I need to know if it's just a little more than 0 or just a little less than 0. Because that determines whether my answer is positive or negative. So this one would be a positive infinity.
How did you get to plug in 3.9 instead of 4.1?
Ah, good question. Somebody answer that.
At the top it says if it's coming from the right, then you do a larger number. If it's coming from the left.
So you can remember that, or you can just say, that's like 4 minus, so I need to subtract a little bit from 4. Number 6.
so what's that?
Plug in 2. 4 minus 2 is 2. 7 plus 2 is 9. 1 plus 2 is 3. Hey, everything's great on this one so far. 2 minus 2 is 0. So I'm headed toward infinity, but I don't know if it's positive or negative. I don't know. I don't want to say yet. Plug in. What should I plug in?
Something bigger.
Something bigger than 2. 2.1, 2.01, 2.0000000001. So the top is pretty close to 2 times 9. And the bottom is pretty close to 3 times, and then here's the one I'm worried about. What do I get when I do 2 minus 2.001?
Very small.
Small, definitely small. Positive or negative? 2 minus more than 2. Negative. So 18 is positive in the top over negative. Some teachers write negative 0, but that feels wrong too, right? Because 0 doesn't, I mean, I know what you mean, and so, I don't know, is small better than writing negative 0? Like, neither one of them is really clear and perfectly accurate. if you put negative 0, I would be okay. Some people do it this way. 0 from the left, which is kind of right. It's a little less than 0. Either way, this one's negative infinity.
Isn't it always going to be smaller?
It's always going to be small, yes. That's why, because what's most important is it positive or negative? That's why we're doing this. It is always going to be, I intentionally wrote it different ways, very small, super small, just small, almost 0. You could put 0 as long as you tell me that it's not exactly 0. It's a negative 0, which again, there's no such thing, but kinda.
So does it just happen to be that there's positive on both the right and the left right now?
No, yeah, there's no, you're looking for patterns, and I like you looking for patterns, but you got to plug in the, and as you get better at this, you're not going to be writing all of this and writing 2 minus, you're just going to look at it and say, oh, it's going to be a little less than 0, so it's negative. For simple functions, you could sketch a graph. I don't know, I think I would still just plug in a little less than 0. 1 over small but negative means negative infinity. Again, if you know what the graph looks like, you can do it graphically. As x approaches 0 from the left, then yeah, you're headed toward negative infinity. So this is just like, if you know the graph, you could sort of switch to doing it graphically, but the chances that you know the graph are probably small. Like, that's probably the only graph like this that you would know. For other one-sided limits, you might get an indeterminate form. For indeterminate forms, we use our normal techniques. Like, there's some calculus stuff going on at the hospital. That's not how you say that. It's l'hôpital, but that's calculus. In fact, that's like second semester calculus. But we're not worried about that. Basically, use the normal stuff. There's our 3 tricks if we need them. Factor, fractions, and conjugates. Factor, fractions, conjugates. Those are the 3 tricks. All right, limits when x is going to infinity. This has a fun little saying that goes with it. We'll do the saying last. I don't want you to understand it and not memorize shortcuts. Because the saying is rhymes, and so if people don't understand it, they memorize the saying wrong, because if you get the words wrong, it still rhymes. So it's like, hey, great saying, but it's so cute that you mess it up because it rhymes. We'll get there in a minute. If x is going to infinity, which one of those terms in the top is most important if x is getting really, really big? Right, 4x cubed. Like, if x is 1 million, well then who cares about minus 19, or even plus a million, or even a million squared if a million cubed is involved. So you're always only looking at the biggest term, the biggest degree term. How about in the bottom, which is the most important term, if x is a gazillion? So when x is really big, all I care about is 4x cubed compared to 5x cubed. Well, what's 4x cubed over 5x cubed?
Just x.
4x cubed divided by 5x cubed. Yes, you're like, wait a minute, that just got really easy. What's happening here? And that's our answer. Because when x is super, super big,
I want this only on the test, just this.
when x is really big, the only thing you have to worry about are the biggest terms. Right? If you plugged in a million, then subtracting 19, who cares? And the bigger number you plug in a billion, 19 matters even less. Plug in a trillion, 19 is, it's already inconsequential. The only thing that matters when x is really big are the biggest terms. Number 9.
Not so nice, but still.
What's the biggest term in the top?
5, or no, the 2.
Yep, negative 2x to the 5th. What's the biggest term in the bottom? 7x cubed.
Can you just make it to negative 2x to the 2 over 7?
So those are the only ones I'm worried about. So if I plug in a really big number for x, maybe I should reduce this.
Yeah, negative 2x to the second, and 7 on the bottom.
Sure, we can do that.
And then it doesn't really.
So what happens if I plug in a really big number? What happens to negative 2x squared over 7? What is it doing? Is it getting really big, really small? Yeah, negative 2 times 5 gazillion squared over 7. We're headed to negative infinity. And negative infinity means D and E, right? We want to keep remembering it's both of those things. So look at the biggest terms and then think about what's going on. So on number 10, biggest term. And when I say biggest term, we really mean highest degree term. So what's the highest degree term in the top of number 10? X to the 5th. And in the bottom, 7x to the 6th. Again, we're looking at the degree. I don't care about the coefficients, just the degree. So this would be approximately x to the 5th over 7x to the 6th, when x is really big. So then that reduces to 1 over 7x. And now if I plug in infinity, one over 7 times really big, since you like using non-numbers today. What's 1 divided by, right? This is if I have $1 in my pocket and I divide it among the 8 billion people on Earth. How much money does everybody get? None. Okay, do you want the saying or do you not even want the saying? Okay, I'll give you the saying, but be careful, it rhymes, so if you mess it up, you're going to mess up this section. Alright, and this is all concerned with which degree is bigger. If the top degree is bigger, let's see, what would you say the limit is if the top degree is bigger? Which case was that, 8, 9, or 10? Top degree is bigger?
Probably
that was number 9. And that didn't have a limit. That was a no. That was number 9. Just if we need to compare it. If the bottom degree is bigger, which number was that?
10.
That was number 10. Bye. And what was the answer? 0. If the bottom degree is bigger, it's always going to go to 0. Right? Because you're always dividing by a really big number. And that leaves number 8. If they're equal, what did we end up using, or what was our answer equal to? The coefficients. All right, so everybody remembers this little saying. The trouble is they misuse it, or they misremember who goes with what. Top no, bottom O equal co. But again, it's so cute that I don't even want to say it, but sometimes people will remember, they'll mismatch them, and it still rhymes, so they think they've got it right. So top no, bottom O equal co, or don't worry about the memorizing the trick, just look at the problem and think about it. All right, your assignment is the next worksheet, so worksheet 3. in the packet. Top no, bottom O equal co. I almost hesitate to show it because calculus students use that when they're not supposed to use it. It's only when x is going to infinity. Maybe I should emphasize that. Because they'll get a problem as x approaches 2, and they'll say, top no, bottom O equal co. Like, no. I mean, I'm glad you remember that, but only as x goes to infinity. Unit, whatever unit we're on, 16. Worksheet 3.